Welcome back to Logic, Language and Information. My name is Jen Davern, and together with Greg Restall, I'll be giving about half the video lessons for this course. So far, in the first group of lessons, we've learned about propositions, namely statements that can be either true or false. And we've developed a formal language for propositional logic that starts with atomic propositions and then builds up complex formulas using the connectives of negation, conjunction, disjunction, conditional and biconditional. What we've looked at so far is the syntax or the set of allowable formulas of propositional logic by specifying the acceptable strings of symbols. We now need to examine the semantics or meaning of those formulas by examining how the truth or falsity of a complex formula is determined by the truth or falsity of its atomic components and of the connectives within it. Okay, so propositions are the sort of things that are either true or false. We'll write 1 for true and 0 for false. Any two distinct symbols would in fact do. T and F are quite common. We'll use 0 and 1 because they are common and because they are also standardly used in digital electronics, one of our application areas. This gives us classical two-valued logic. In more advanced courses in logic, one may study so-called non-classical logics with more complex semantics which allow more than two possible truth values. For example, in a three-valued logic, one has the values 0, 1 and a half, where a half usually means not sure, while in fuzzy logic or probability logic, the possible truth values include all the real numbers between 0 and 1, all the decimal numbers, infinitely many of them. In the philosophy section of this course, we'll briefly discuss some of these non-classical logic. So suppose we have a complex formula built out of 3 atomic propositions, P, Q and R. Then in fact, there will be 8 different combinations of truth values transmitted to that formula. To see this, we see that P can take 2 possible values, 0 and 1, and then our next atomic proposition Q can be 0 or 1. That gives a total of 4 combinations for 2 atomic propositions. And then when we add the third, it can be 0 or 1, to give a total of 8 combinations of truth values. In general, if we have n many atomic propositions, then we'll have 2 times 2 times 2 times n times multiply, which gives 2 to the power n many different possible truth combinations. This quantity, 2 to the power n, grows very fast indeed as n gets larger. For example, for just 10 atomic propositions, we'll need more than 1,000 different truth combinations, while for 40 atomic propositions, we're in the range of 1 trillion different truth combinations, which would take terabytes of data to store. This exponential growth is an advance warning that we will have to find smart ways of analysing and manipulating propositional formulas, because the dumb way of listing all possible truth combinations will not be practical. In the computer science application section of the course, we will see some database examples with more than 40 atomic propositions, but we will use smart ways of manipulating the formulas. In this course, we'll get you to work by hand on truth tables only for 2, 3 or 4 atomic propositions. So truth tables that have 4, 8 or 16 different rows of truth valuations. To set out a truth table for, say, 3 atomic propositions, an orderly way to do it is by listing the atomic propositions in order from left to right, P, Q and R. Then to systematically list all the 8 combinations of truth values, a clever way to do it is vertically rather than horizontally. Start with the leftmost atomic proposition P, and we're going to write zeros in the first half of the rows, the first 4 rows, and then write 1 in the second 4 rows under P. Then for the next atomic proposition, we will go down the rows by 2s, a quarter of the total, giving the first 2 rows zeros, the next 2 rows 1, the next 2 rows zeros, and the final 2 rows 1. For the rightmost atomic proposition R, we'll simply alternate 0, 1, 0, 1, 0, 1 down the 8 rows. If there were 4 atomic propositions, then we'd start in the leftmost column with the first atomic proposition by writing 0 in the first 8 rows, and then 1 in the next 8 rows, and after that continuing as we did for the 3 atomic propositions. The result is a table in which the rows of truth valuations are in numeric order in binary number notation. This will come in rather handy in the digital electronics application section of the course. For you to do your working by hand, we'll make available for printing blank tables like this with all the truth combinations already written out. So in the next lesson, we'll get down to the business of the semantics and start with the truth table rules for the easy connectives of negation, conjunction and disjunction.